So this lesson is going to be about superposition, and simply put, superposition just means that you add two waves together if they meet some certain conditions. Now, looking at it from a broader perspective, superposition can always occur in the same type of waves. The only condition that is necessary is that the waves should be of same nature. For example, if you're doing superposition for light, the other wave should also be light. If you're doing superposition for sound, it should be sound waves from both sides. If you're doing it with water, it should be water from both sides. So superposition, simply put, will be addition of two waves or more than two waves meeting at a point. So at this level, at A levels, we are just going to go about superposition of two waves, mainly coming from similar sources, so that they are at least coherent. At least we have the guarantee that they are coherent. In nature, they don't have to be coherent. At least superposition will still take place. Okay, so monochromatic, two terms that we are supposed to be familiar before going ahead. The first one is going to be monochromatic. Mono means single and chromatic is short for lambda or wavelength. So monochromatic would mean that the sources that you're using have a single wavelength. For example, if you're dealing with light, then if you're introducing, let's say, 600 nanometers, then a 600 nanometer means that from the other source, the wavelength is also 600 nanometers. Okay. Now, to make sure of this, what we do is we use a single light source for the experiments, and then we add two gaps in front of them to make sure that they are exactly 600 and 600. We don't use two different light sources. Okay. All right. Then we have to understand what is coherence. Now, in A levels, coherence will mean that they have identical frequency, at least, and their phase difference is constant. Either it's zero or either it is constant. What do we mean by that? It means that whatever phase difference, for example, between one wave and two wave are, if you match them, you will always find that at one location, one is at the peak and the other one as at the lower point. And the other location you match it, one is at the lower point, one is at the peak. So throughout their lifetime, they're going to maintain this relationship that they have between each other. The phase difference is going to remain constant. It cannot change. But if you look at the other example, you will see that over here, we can see that at the very first part of the wave, they are somewhat similar. Okay. But at this location, we can see that it has stopped being coherent, or it has stopped being keeping its phase constant in reference to the other one. It is always changing its frequency, or its frequency is changing at all times. So this is not coherent anymore with the first wave. Okay, so coherence will only mean that there should be no discrepancies like this. There should be no change in phase between the two waves. If it is constant, it should remain constant. Okay, let's look at this from another perspective, like this one. So if the waves are moving like this, the angle between them should remain same. So for example, the phase difference that we've understood in the previous video, this is the phase difference. Okay, so this phase difference should remain constant. So phase difference should remain constant no matter how the waves are moving. It doesn't matter. Whenever they are going, wherever they are going, it doesn't matter. They should remain constant. So if I play this animation, the waves are still moving ahead. And if you stop at this point, we realize that the phase difference between them is still the same. The phase difference is still the same. When they were here, for example, the angle between them was, let's say for the sake of example, that was 90 degrees. Over here, it is still 90. So this is what constant phase difference, or you can say coherence, basically is looking for. They should be coherent. Okay. So let's go back to the lesson. All right. So we understand what is coherence. Okay. All right. Now we move towards interference. So interference, as the word suggests, two waves will be meeting at a single point, and depending upon their instantaneous amplitude, we will see whether they're going to get added together or whether they're going to subtract it together. So the addition of the waves is called superposition. One of the wave is being superimposed on the other one, and as a result of that, interference occurs, right? And what type of interference there may be? There is constructive interference, and we have destructive interference. So in constructive interference, what happens is that the wave actually matches the other wave in amplitude. So what could happen, how this interference could take place? Either two waves are moving in the same medium or towards the same destination. So what will happen at this point? Or either they're moving in opposite direction. For example, one wave is coming from this point, one wave is coming from this point. The resulting wave will be formed as a result of superposition. And the process of interfering with each other at the point of meeting is simply interference. Okay, so let's try to superimpose these two waves depending upon their amplitude. So we can see that at the very beginning, at this point, they approximately have an amplitude of a bit higher than 0.5. So if I consider this to be my zero axis, this is my mean position, and let's say this is 1 and this is 2, this is -1, this is -2, then my total amplitude, if added together, since both displacements are positive, for the sake of example, I'm taking them to be 0.6 and 0.6. So over here, at this instant, at exactly this instant in time, I will get a value of 1.2. At 0, it was 0. 0 plus 0 becomes 0. So then when I reach the 90-degree angle, I realize that both of them are actually 1. Okay, so add them together to at this 90-degree angle or 90-degree point, they become 2. 1 plus 1, 2. Similar thing will happen at the rest of the wave as well. So instantaneously, at very instant, the amplitudes are added together and we get the resulting wave. So the resulting wave, and let's look at this 270 degrees. So at 270, we can see that both of them are actually residing at -1 value. So at this point, we get -2. So if we add together at 180, you can see at 180, it is 0. So now we can guess what the shape is going to look like. And at 360 point, we can see that it will come back to 0 again. So the shape is going to look something like this. So you can see that the individual amplitudes have been added together. And please be advised that this is happening at one instant at a time. It can't be done in this lesson. It's not possible to do at this level at least. But every single instant, at every single time, whatever that amplitude is, it is being added with the second wave and the resulting wave is being produced. So that is how you visualize it. Okay. Then we have destructive interference. And this interference, you need to understand that this is a complete destruction of the wave. The output should be 0. Only then we can call this to be a destructive interference. You will see in some situations in the following videos, you will see in some situation the constructive interference will still occur. There will still be an addition of amplitude. The destructive interference, there is a misconception between students that, for example, if we add two waves, this is amplitude A, and let's say you add with an amplitude opposite to this one, the 2A and A. Now we can see that adding these two waves together, the maximum amplitude we're going to get over here is going to be -A, as this is actually -A and this is +A. So if you add this section with this one, you get -A because 2A is in the negative, right? So you might think that this addition that we've done with a negative value has resulted in a negative amplitude. This is destructive interference. No. This is not destructive interference. This is still constructive interference, because for the destructive interference, the amplitude should exactly be 0. The waves should be exactly opposite to one another with the same amplitude. So this should have been A as well. If this was added, let's say, with a wave that has an amplitude of A, with an amplitude of 180 phase out of degrees with -A, then this gives you a 0 answer. This is destructive interference. If there is any amplitude left after the addition, be that due to addition, be that due to subtraction, due to the output sign of the wave, that will not be considered destructive interference. For destruction or destructive interference, the amplitude should be exactly 0. So let's try to do this one. I'm going to just do this quickly over here. So 90 degrees, 180, 270, 360. This is where we're going to test them. So 0 and 0 at this starting point, this gives me 0. So this is my reference line at the very center. Then I move to 90 degrees, I realize that one of them is 1, and at 90, the other one is -1. So what amplitude do I get? I get 0. Similarly, at 180, both are 0, so 0 plus 0 gives me 0. At 270, I realize that this is -1, and this is a +1. So I get 0. At 360 and 360, I get 0 again. So the resulting wave has actually been destroyed completely. The amplitude is 0. This is what destructive interference should look like. The amplitude should be same and they should be out of phase. You can see that if this region is positive, this is negative, and if this is negative, this is positive. So they're completely out of phase of one another. Just a small extra information. This is how noise cancellation headphones actually work. What they're doing is they're picking up the background noise. There is a processor inside of them that actually makes it 180 degrees out of phase and then adds into the voice, and then it processes that video through the through that audio through the speakers, and you listen to it. So it is actually gathering sound from the environment, turning it opposite, and then adding it to itself. That is how noise cancellation works. Okay. Now, phase difference, we've already done phase difference in the previous lesson as well. I'm just going to go through this briefly, how to find phase difference and what is phase difference. If you go towards this idea, we realize that a simple wave can be represented as a unit circle, right? We can see that there is a circle, unit circle, representing a wave, or a circular motion in this way can be represented as a wave. So if you were to find the phase difference between two waves, you will realize that this is what it looks like. So two waves moving out of sync of one another. One of them is leading, one of them is lagging, and their vector representations on the circle is going to look like this. So if you were to find out the phase difference between them, what you do is you take this difference, let's call this delta t, divide this with the time period of any one of the waves, because we believe that the wave time period for green and purple both is exactly the same. So either you pick it from purple, either you pick it from green, it will be the same. And multiply this with 360, whatever angle you get is actually the angle between the vectors that is represented on the phase over here, right? So this is phase difference, and it can be represented in two situations or two methods. So either you find or represent this angle, let's say this angle is 80 degrees, or let's say it is 60 degrees, right? For the sake of example, this is one of the answers. The other answer will be on the outer side. So if you can't find this option, you can also have mentioned, you could have also mentioned 360 degrees. So 360 or the central angle 60, both are phase differences found by this formula. So I believe we understand what phase difference looks like, and let's play the video again and see what that animation is actually representing us. So there is a phase difference between these two waves like this. Okay. So if we had to figure out phase difference over this point, we can choose 0 point of this one and 0 point of this one. The delta t comes out as 0.2. Divide this by time period of any one of the wave. Now choose either wave P or wave Q, because they are going to have the same frequency. Their time period will be the same. So I choose wave P because it looks simpler up to 0.6 at this point and at this point. So the time period is 0.6. If you wanted to choose wave Q, that's your choice. That would also give you the same answer. Now I can see that wave Q ends at 0.8. So one trough and one crest, it starts at 0.2. ends at 0. If you take the difference, this is also going to be 0.6. So that's what I've been saying. The time period will be the same, no matter you pick it from whichever way you are comfortable with. So multiply this with 360. Your answer will come out as, I think, 120, probably. You can try this, divide by 0.6, multiply by 360. This, yes, 120. So the answer is 120 degrees. The phase difference between them is 120 degrees. Okay. Similar question has been done in the previous video as well, but I'm going to solve it again for this video. So for anyone who's watching this video for the first time. So we can very clearly see that the phase difference between the waves is actually 100 degrees, but 100 degrees is not mentioned in the question. It's not given in the option. So I told you that the other option that you could have done is that you can choose the central angle, which you find from the formula. Either you can choose this angle, or either you can choose the outer angle. So what has happened is that the central angle is given to you as 100 degrees in the question, but it's not in the options. So then at 100, or you can say 360 minus 100 that you found is equal to 260. So the outer angle looks like 260 degrees. So either 260 is the answer, or either 100 is the answer. If you don't find 100, you'll find 260. If you don't find 260, you'll find 100. We can see that we found 260 as well. Okay. All right. Moving on to this concept, that is path difference. Now, to understand this idea, to understand path difference, what's the main problem? The problem is that doing this constructive interference and destructive interference at every instant in time at one single point all the time is mathematically and visually speaking is going to be tiresome. It's not advisable to do that all the time. For a question that we only have 30 to 40 seconds to figure out, to solve, this technique actually proves to be a bit more hectic. It requires more time, it requires more effort. So what we've done is we've developed this technique of path difference to understand whether there is going to be constructive interference or destructive interference. Now, to visualize this first, what type of interference this is happening or this is actually taking place, first we need to see a video of superposition of water. So here we have two sources of water. First, we will only see one source of water creating waves. So these are wave fronts that we are seeing right now. Okay. Now, as soon as we turn on the second source of water, you will see the interference pattern, what's actually happening. Now just wait for that. Now the second source has started to work. Now this pattern that you're seeing on the screen is actually the interference pattern of two sources. Okay. We have two sources over here. Now, how is the wave actually moving? The waves are actually moving in this way that these lighter colors are actually the crests. This is crest, crest, and crest. And the darker bands are actually the troughs, troughs, and troughs. So if I had to draw this wave over here, it's going to look something like this. Trough, crest, trough, crest, trough, crest, trough, crest, trough, crest. If I had to look at it from the side, right? Now, since this wave is being formed over here, we will see that this is actually constructive interference. This is constructive. Over here, we can see trough, crest, trough, crest, trough, and so on. This is also constructive interference because wave coming from this source and wave coming from this source, they are all meeting at this point where the phase are same. The crest is meeting with crest. The trough is meeting with trough. So we see a constructive interference. And over here as well, we can see that this is, let's say, trough, crest, trough, crest, trough, crest, trough, crest. Why has this happened? It has happened because of the constructive interference concept, which we just did, that individual amplitudes will be added together. So over here, we can also see that this will also be a place of constructive interference. Now, where are the places where we see that the destructive interference has taken place or there has been no wave? Notice these lines of sight which are exactly blur. What has happened here? In these sections, the destructive interference has taken place because there is no output. The destructive interference has taken place. There is no output. The waves have completely destroyed each other, right? Because one of the waves had amplitude positive and one of them had a negative amplitude. Now, this idea is further understood. Now, you can observe this pattern right now. This is basically a two-phase, or you can say two-source interference, what it is supposed to look like. Okay, when we go back again over here at this point, this is what's going to look like. Now, I'm going to show you another animation in which this two-source interference is going to actually take place. Now, we have two sources, just like over here, for example, over here, just like over here, we had two sources. Now, we are repeating the experiment with two light sources, just to observe what is constructive and what is destructive interference. This is actually a double-sided experiment. I will make a separate video for this, but just observe what's happening with two sources. So we have two sources producing waves like this. Now notice at the points wherever, just let it run for a while, before it hits the screen. Okay. Now notice what's going to happen. Okay. Now we have crests and trough inbuilt to the system. Okay. So you can notice that at these points, and at these points, the crest of both waves are matching together. Okay. So because crest and trough are matching together, you will see that the pattern is actually vibrant. So this interference that you are going to see on the screen is going to be constructive. And where you can't see the wave, for example, you can't see color, this is a destructive interference. And you will see that for the destructive interference, you will see this region in which one crest and one trough are being added together and they're just completely destroying each other. So for the sake of understanding, let's let this animation to run. Let's see what happens. So notice what has happened. The phases which actually match crest and trough are in sync, are in line with each other. They are producing a bright color. And where the phases are out, for example, one is crest and one is trough, the phases are not adding together and it's producing a destructive interference. To visualize exactly this issue, to visualize exactly this problem, you can say it's difficult to do this on paper at all times. You can't do this again and again. You can't make this circular wavefronts again and again, right? So what we have done is we've devised a method of this path difference to actually figure out whether this section or this section or this section or wherever they are going to meet on the screen is going to be constructive interference or is it going to be destructive interference. So figuring this out is actually the main thing. And we're going to use this technique to figure that out. But for this, you'll have to see the next video, which is about Young's double slit experiment. So all the difficult type of questions, all the different ideas, all the different thought processes are going to be discussed there, because we have double slit. We have two sources. Just like this situation, we have two sources, and we will discuss the rest of the lesson, the rest of the part in that part. Okay, that is, I think, part number 7. Yes, that is part 7. You will find the part series in the description as well, from part 1 to part 9. I would advise you to watch this whole video, this whole playlist section wise, part 1 to part 9. I've organized them in such a way so that you can fully understand this chapter and what are the requirements from the student to visualize how to look at waves and how to solve its questions. That is all for this lesson.